today's discussion topic, or today's topic for elucidation, is going to be the dark energy survey. Now, I have not kept myself up to date with all the results from the dark energy survey, so this is going to be a description about the design of the dark energy survey, what it is, why we care, what we're doing, and how it was put together, what the observations it's going to make, how it was motivated, that kind of stuff. So the dark energy survey will go into the design and the details of the survey and what kinds of measurements it's geared. It's designed to make certain measurements, and it's capable of making other measurements that are outside the central science scope. But we'll get into that as the time goes on. But first of all, we need to look at the dark energy survey. So this is a cosmological survey. Here's the logo. Here's the logo right here. It's built as a camera. The DE-CAM is the dark energy camera, gigantic camera that was housed in or attached to the 4-meter telescope at CTIO. So that's a telescope in Chile. It's the Blanco telescope in Chile. So what happened was, way back in the day, like 15 years ago, I think it's NOAO that runs this telescope facility in Chile, said, we have this big telescope, we don't really want to use it, or we don't have any instruments that have been on it. The instruments we have are a little bit out of date, so we're going to accept proposals for someone to build a new instrument to go on this telescope, and you will get some amount of time, like 300 nights a year, some gigantic amount of time, to use your instrument for what you want, and then you'll open it up for the community to use the balance of the time. Some kind of deal that was worked out like that, where you get most of the nights to use your instrument to do the science that you want, and then you open it up for other people to use the instrument, and they can subscribe for time. And it's a way for these kind of older telescopes to repurpose themselves with updated instrumentation. Because the mirror itself, the mirrors don't really wear down, but the instruments do. Instruments wear out, they get outdated. And so you have to keep your instruments up to date, and the telescopes can last essentially forever. I mean, you can always recode a telescope with a little bit of aluminum. So that's what this design was for. This is after the Sloan Digital Sky Survey. So the Sloan Digital Sky Survey ran from 2000-ish to, it's still going on now. They're still using the telescope to take new measurements. But early on, a number of measurements were made in cosmology from Sloan Digital Sky Survey, from the cosmic microwave background radiation, and from the supernova measurements that had discovered dark energy. And so the Department of Energy, the US Department of Energy, along with other people, so we can look at who is actually on it. Here's the collaboration. We will find that on the collaboration includes all these people. But of particular interest is what am I looking at? Here we go. Collaborating institutions. So the Department of Energy through Fermilab, the University of Chicago, because Fermilab and the University of Chicago, when it comes to cosmology, it's essentially the same group. There's a lot of people who have joint appointments between Chicago and Fermilab. Anyways, a variety of these things. Argonne National Lab, it's another Department of Energy laboratory. SLAC right here at Stanford, that's another Department of Energy laboratory. So there's a bunch of people that got together. It's provided by the U.S. Department of Energy and the National Science Foundation. This was all geared towards understanding the properties of dark energy, and in particular, understanding a quantity called the equation of state parameter. So dark energy is this material or substance or effect, because we don't really know what it is, that causes the universe to accelerate in its expansion. And there is a property of this that's called the equation of state. The equation of state is the relationship between basically the density and the energy. Or the best example of an equation of state that people are usually familiar with is the ideal gas law. So the ideal gas law is an equation of state. It's the thing that says PV equals NKT. Or if you're a chemist, it's nRT, but we're not chemists on this channel. We are physicists, and so we use K. That's a K, by the way. And so if you just rewrite this a little bit, you get P equals N over the volume is the density, rho KT. So it relates the pressure, the density, and the temperature. this is an equation of state. So it's a relationship between variables like pressure, density, temperature, and et cetera, and so forth. So the dark energy also is going to have some equation of state, and you write down what the equation of state is, and there's a parameter in dark energy theory that is this parameter called omega. So the dark energy has an equation of state, excuse me, and one of the parameters in the equation of state is omega. And that omega has a value. It's going to have a value, some number, and the assumed value, if there's a cosmological constant, like Einstein's cosmological constant is a real thing, then this omega is equal to -1, okay? But it could be something else. It could be a value bigger than -1, it could be a value smaller than -1. -1 is what you get if it's kind of the most generic, boring dark energy phenomena that you can think of. So this equation of state is going to tell you whether the expansion rate is going to change, if it's going to accelerate faster and faster and faster, or if it's going to slow down the acceleration, is going to be given by this. So this is something that we want to measure. What does the future have in store for us? Because if you have an equation of state, this omega is less than -1. So if omega is equal to -1.2, then bad things will happen in the distant future. The universe will accelerate faster and faster and faster, and it will rip things apart, and eventually galaxies, like the strength of gravity, the gravity that holds galaxies together will not be sufficient to withstand the accelerating expansion of the universe, the increasing acceleration of the accelerating expansion of the universe, and galaxies will fly apart, and then eventually the nucleus will, atoms will fly apart, and then the nucleus get ripped apart, and then we'll all get ripped apart. It's called the Big Rip, and we're all dead. So that'd be a bad thing. And then you also could have a situation where omega is like -0.9 or something like this, in which case, depending on the dark energy, acceleration would slow down, and eventually you could imagine the universe collapsing again if there's enough matter in it to pull it back together. So the standard model, or kind of the generic model, is the dark energy equation state parameter being -1. So that's what they want to measure, is what is this dark energy equation of state parameter. So you have to measure the expansion rate of the universe as a function of time to see if this value is something other than what we currently observe. So the dark energy was discovered in the late 1990s through the supernova measurements. Those measurements were refined. We know that the universe is flat because of the cosmic microwave background radiation measurements. So that's something else that we've talked about, that we know that the universe has all of the total energy density in the universe is equal to the critical density. It's some quantity that's normalized to 1, which means that when you add up all the energy density components, you get 1. So that includes regular matter, includes dark matter, includes dark energy. So all of those things together add up to 1. That is, we get primarily from the cosmic microwave background radiation and the hot and cold spots in the cosmic microwave background radiation. And then we have the total amount of dark matter in the universe, and we get that from the clustering properties of galaxies, and we can infer the presence of dark matter from galaxy rotation curves and things like that. So all of these things, we live in one universe, so they all have to hang together. And understanding these properties is important, is what the Dark Energy Survey is designed to measure. Let's see, am I excited about Roman? I do. I think it's going to be pretty gnarly. The Roman telescope, which used to be called the Sloan, used to be called LSST, the Large Synoptic Survey Telescope, was renamed the Nancy Grace Roman Telescope, I think. So, yes, that will be a cool instrument to have online once it comes online. All right, so this is the Dark Energy Survey. It's supposed to be like a 4 or 5 year survey, and built at Cerro Tololo, CTIO, Cerro Tololo Inter-American Observatory in the high Chilean Andes to carry out the project. Now that right there, so we're going to look more closely at that. So that is the Dark Energy Camera. So let's take a look at the camera first so we can see what it is. Oh, W first to Roman. So I apologize, I was wrong. LSST is, what's LSST? That was named after Vera Rubin. LSST is Vera Rubin. W first is Roman. So I apologize for that misunderstanding or misidentification on my part. Okay, so the Dark Energy Camera. This is what the Dark Energy Camera looks like. It's extremely heavy. It's like as much as a car. And it was built on, so here's some people putting it together. They had at Fermilab, where's the Fermilab thing? It's not showing up. So dark energy camera, Fermilab. They assembled it at Fermilab. It has a variety of CCD chips. These CCD chips are designed to be sensitive in the infrared part of the spectrum, like to have good sensitivity in the infrared part of the spectrum. The problem you have with most CCDs is that the CCDs generally are really good in the visible part of the spectrum and in the near kind of ultraviolet. But when you get into the infrared, their sensitivity drops off because they're lower energy photons that are hitting you. And as a consequence, it's harder to dislodge the electrons in the CCD camera. So these are designed to be CCD chips that are better in the infrared. The infrared is going to become important in a moment. Once I am able to show you what it is I'm looking for. Is this what I'm looking for? Yeah, okay, so this is inside Fermilab in this building that used to have the holographic bubble chamber, and in fact has like pop cans in the ceiling. So let me go to the map of Fermilab. So Fermilab outside of Chicago, national laboratory thing where they put this camera together. This is the Wilson Hall, the main building on campus. Right there. If we drive down this street, past the Feynman Computing Center, keep going down the street, you arrive at the building right, where is it? Right here. Let me zoom out. It's like, oh, here it is. The Silicon Detector Facility, SIDET. Okay, near SIDET is this weird-looking building. Here's the weird-looking building. It looks a little bit like, I don't know, like the top of a virus. Although there's another building called the Proton Pagoda that looks even more like a virus because it has a double helix spiral staircase that goes down, but that's not this building. So this right here is the holographic bubble chamber. That is an old particle detector that was built in the 1970s, 1980s, used, and it was housed in this facility. The particles would come and hit it. You'd see streaks in this bubble chamber. And the roof of this building here, where they housed it, is filled with pop cans, like smashed pop can lids. And of course the roof leaks. All the roofs that were designed by Robert Wilson leak. But they look cool. So they look cool, but they leak. So this building is, when they built the dark energy camera, they put it in this building, and it had a support structure that we can see right here. Hopefully this one shows up. That's the camera itself. Here we go. Okay, so it's kind of low resolution, but there you go. So this is the interior of that building. You can see all the pretty colors, and this is just some structure that they had in order to put the camera on it, plug all the cords in, see if they could maneuver it around and how things would distort, and can we get the cabling in the right way so that the camera is uninhibited as it tries to survey the sky. So that's what this structure was built for. I was originally, or back in the day, we thought about designing this, using this structure to do a paraphoton search using the sun and tracking the sun by putting some kind of tube on here, but that experiment never eventually died out. Nevertheless, this is the dark energy camera as they were testing it. So they built all of these, they had the CCD chips that they wanted to use, designed specifically for this system. They built a whole bunch of extras, and then they tested them in this SIDET building. They tested all these chips to make sure, like, then they could separate out the engineering grade ones, like ones that we can just, test software on or whatever, and then the science grade ones. The science grade ones, because you're always going to get variation in the quality of the CCDs that you get. So as they tested all of these CCD chips, they would separate out the good ones, and then the less good ones. They were all, state of the art, but you separate out the ones that have the best noise properties and so forth. And when you actually build the detector, you are going to use the best quality ones that you have available to you. And instead of just having really strict constraints on it, it's easier to just say, make a whole bunch of them, and then we'll just take the ones that are the best, that are statistical fluctuations above the mean. So there you go, 72 blue tinge sensors to detect the light. I can't remember the size of the camera. It's like 500 megapixels, I think, is the size of this camera. Yeah, 570 megapixels. That is a lot of megapixels. It's like half a gigapixel camera. So there we go. That is what the dark energy camera looks like. It weighed a huge amount. Then they transported it down there. There was one guy whose job was to make sure that it got shipped. Like his job was to make sure that the camera, the logistics were in place to ship this camera from Fermilab where it was assembled down to the boat, down the Mississippi River to the boat somewhere, and then from there to sail down to Chile and then offload it and then drive it up there and then make sure that you don't put the camera, you have infrastructure available there to lift this camera to attach it to the telescope, because this was also the largest telescope that had been put on the Blanco, the largest instrument that had been put on the Blanco. So if we look at the Blanco telescope, dark energy camera on the Blanco, which is going to be these other images, here is what it looks like. Okay, so here's the structure. We might as well look at this image very quickly. Okay, here's the structure of the camera. It's got this gigantic lens. I think at the time, I don't know if this is still true, it was the largest lens ever made, 1.2 meter lens. And it corrects for spherical aberration and all sorts of things, directs it to the camera on this gigantic hexapod structure to hold it steady, because as the telescope slews downwards, then you have all this weight and it's going to distort things, and so you have to correct in the software for the distortion of the telescope as it goes down. This is what it looks like, I think, mounted on the Blanco telescope. Okay, so here's like the counterweight. There's the mirror. Mirror's right here, back there, and then the camera is pointed, so it's at prime focus. The light comes in from the sides of the camera, hits the mirror, and then is reflected back into the corrector, and then the camera's basically right here. You have all this cabling that comes down, and here's the hexapod. It's got should have 6 legs. Oh, the hexapod is actually a structure that's in here, so never mind. That's something else. Anyways, there you go. So that's how this thing is set up. It's designed to have a large footprint. So the camera is so big, it's 470 megapixels or 570 megapixels, because you want to take big images of the sky. You want the images to have a large footprint because it's a survey of the sky. You want to survey as much of the sky as possible. It has a survey footprint that we will take a look at. So dark energy survey footprint. The mirror was already there. So the mirror was already on the telescope. The telescope was already there. They just needed a new instrument to put on the telescope, and they had to reinforce it. So it looks like here's the dark energy camera tank, or the dark energy survey tank. Open image in new tab. That's what the survey looks like. Now, a few things about this survey footprint. This stripe right here, the gun of this tank, is I believe coincides with stripe 82 from the Sloan Digital Sky Survey. So the Sloan Digital Sky Survey was run out of the Apache Point Observatory in New Mexico, and it had a stripe along the equator that they visited multiple times. As stripe 82, it was really important because you survey it multiple times, then you add all those images together, and you can get kind of deeper images. You can see things that are fainter. And so they lined this part of the survey up with stripe 82 because they already knew where the targets were and so forth. And then down here you have the rest of the survey footprint for the dark energy survey. At the bottom end of this thing there was another survey that was being done from the South Pole Telescope, and they wanted to match the South Pole Telescope. They wanted to get data from the South Pole Telescope, which is, I think, even farther in the infrared. And that would be another interesting stream to do, is like the South Pole Telescope and maybe other science that's being done at the South Pole. And it overlaps with this bottom part down here, so that they can get an even wider spread in the portions of the electromagnetic spectrum that they're surveying. So that's the survey footprint for the dark energy camera. What the survey is designed to do is measure, again, the properties of dark energy, to look at dark energy. Here we go. This is an interesting image. This shows the South Pole Telescope footprint right there. So that is the survey done from the South Pole Telescope. This is stripe 82 from Sloan Digital Sky Survey. Can I open this up in a new window? I'm sure that I can, and so I'll do that. Here's stripe 82. These DO4s and stuff like that, I'm not exactly sure what those are for. Those are probably some other kind of survey. And then South Pole Telescope is this chunk right here. So they're going to get more. They have different pass bands for the South Pole Telescope. that will interleave with the filters that are on the dark energy survey camera itself. Okay, so there are 4 fundamental measurements that the dark energy survey is going to make to measure the properties of dark energy. These 4 things are, number 1, supernova. Oh, I gotta flip my thing around. Number 1, whoops, that's not what I meant to do. Okay, number 1, supernova. That says supernova. So supernova is one thing they're gonna measure because that allows them, that was the original thing that gave them measurements of dark energy to begin with. Was the discovery of dark energy was from supernova. Number 2 is baryon acoustic oscillations. So baryon acoustic oscillations, we'll talk about that. We'll talk about the supernova. Number 3 is galaxy clusters. Clusters, that's an L. That says clusters. I guess there's a T in here somewhere. There, galaxy clusters. And number 4 is weak gravitational lensing. Weak lensing. There, that says weak lensing. All right, does the universe vibrate? It did back in the day, but it's no longer driven by gas pressure, so it doesn't vibrate the same way that it used to. Okay, so let's go through what each of these things are and how they can tell us about the composition of the universe and so forth. 2 things in particular that are interesting are the supernova results, which we've talked about already because that was the discovery of dark energy. This gives you what is called the luminosity distance. Luminosity distance comes from the supernova measurements. Baryon acoustic oscillations, on the other hand, that is, this gives you what's called the angular diameter distance. Angular diameter, that says diameter, distance. And those are going to be 2 things that are important. And then galaxy clustering, weak lensing, those are also important, but we'll get to those in a little bit. All right, so the supernova data, what they're going to do is they're going to take this telescope, and as they survey the sky, they're going to look for certain galaxies, well, certain targets, to get brighter over the course of about a month. They get brighter, and then they dim back down. Those come from supernova. So if we look at type 1A supernova, there's very famous images of these. The one that I always show is this one, because you can see this one single star that's about 1.4 solar masses blowing up right here and outshining or shining comparably bright to the galaxy as a whole that it's hosted by. So that is a type 1A supernova. Those are standardizable candles. We know how to calculate the intrinsic brightness of a type 1A supernova given the right observational parameters. So we can see how bright this gets, and then we can measure how far away this galaxy is, or what the redshift of the galaxy is, and as a consequence we can measure the brightness of objects as a function of distance. So the redshift that we get from the galaxies is how fast they are drifting away from us. So if everything in the universe is moving apart from each other, more distant objects will be moving at greater speeds because everything is moving away from everything else. And so if you're twice as far away, you have to move twice as fast through the expansion of the universe. And so that gives you a redshift, a cosmological redshift. So as we measure the redshift of these different things, we can measure the brightness of the supernova and then use geometry, special geometry, to determine what the luminosity distance. One thing that I need to point out about the redshifts that you get from this, yeah, go ahead and share the link, that's fine. So the redshifts that you get from the dark energy survey are not the same that we got from the Sloan Digital Sky Survey. So the Sloan Digital Sky Survey had those plug plates. And I found where they were. So back here, this is a Sloan Digital Sky Survey plug plate. Let me go to a slightly different view. We'll go with, which one? This one right here? Well, it wasn't supposed to do that transition, but it did. Okay, so this is a Sloan Digital Sky Survey plug plate. What? There, okay. Okay, so I'm here. This is me. Here's the Sloan Digital Sky Survey plug plate. You can see all the holes in it. So the plate itself is designed to bolt to the telescope at Apache Point Observatory. It has all these holes. Those holes are found. These are the locations of different targets. They could be stars, or they could be galaxies, or they could be whatever, but those are really the only options you have, stars or galaxies. And they drilled holes at the locations, so they found them they took an image of the sky, found the targets that they wanted to look at, and they drilled holes in these locations in order to plug fiber optic cables into all these different holes. The fiber optic cables are shown here. So they're divided into sections with some number of targets in each one, and then you plug them all in, and then they test them to make sure that they're plugged into the right spot. This is a plug plate for the Sloan Digital Sky Survey. So 1 million galaxy redshifts and about 1 million stellar spectra were taken using this. The reason that they needed to plug these things in with fiber optic cables was to measure the spectrum coming from the targets in order to get the redshift. They want to measure the spectrum in order to get the redshift. So you take the spectrum of light from the given object, you look at where the spectral lines land, and then that tells you how much they've been stretched by the expansion of the universe, and then that gives you the redshift, which is basically kind of the drift velocity that it has because of the expansion of the universe. That's an important quantity in doing these measurements. So Sloan Digital Sky Survey used spectra to do that. The Dark Energy Survey does not use spectra to do that. The Dark Energy Survey instead does what's called photometric redshifts, and it does it in a special way that I'm going to show right now because of how amazing it is. I'm looking for this screen. All right, let's see. I have it in here somewhere. Okay, right here. This is an image of the spectrum that you get for different galaxies. Okay, so here's a galaxy at some particular redshift. So this one's at redshift 0, z equals 0. This blue one is at redshift 0. So that means it's like the local neighborhood. This would be like what you get from the Andromeda galaxy or from the Milky Way galaxy, something like that, something nearby. This is the spectrum you get from a galaxy, and there's different features from this, that, and the other particle, or this, that, and the other chemical element. Okay, and in particular, there's this really sharp transition at 4,000 angstroms. And of course, I don't know why we use angstroms. Some people use angstroms. Okay, it's 400 nanometers. There's a 400 nanometer break right here that comes from the absorption of certain kind of bit of chemicals that makes this transition. But there's a big transition in the brightness. You can see that here's the brightness down here, and then it jumps up, and that's this brightness right there. So that is the spectrum. The blue is the spectrum that you get for a nearby galaxy. If you go to redshift 1/2, which means that everything has expanded by 50%, you'll notice that this 4,000 angstrom break has shifted now to 6,000 angstroms. Okay, so that break is now, so here's the lower thing, and then there's that break, and then here's the upper thing. So the redshift, as the galaxies move apart, the light stretches out, and that shift goes from 4,000 angstroms at redshift 1/2 goes to 6,000 angstroms. At redshift 1, it goes to 8,000 angstroms, or 800 nanometers. So that's in the red. Okay, so here is that feature in particular. So that's the one that is most prominent, that allows them, the scientists, to make these measurements, is this break. And you can see how it, as you go to more and more distant objects, and the light has spread out more and more, that feature goes from 4,000 angstroms to 6,000 and 8,000 angstroms and beyond, just like Buzz Lightyear. It goes beyond redshift 1, and you get out here. Also shown on this are the pass bands of different filters. So the green filter is only able to detect light in this fairly narrow 150 nanometer wide range. So it allows light in at 4,000 angstroms, and then it drops off again at 5,500 angstroms. And then you have the R filter, R right here, that picks up right next to that. So green, R, and then I is basically infrared, very near infrared, but I. And then the Z band, and then there's the South Pole Telescope adds a couple bands past this, like I and J or something like that. I don't know what they are exactly. So what you do is you then take an image of the galaxy in the green filter, and you compare it to the same image of the galaxy in the red filter. The green filter is going to pick up this part of the spectrum right here, and the red part is going to pick up this part of the spectrum there, and then the I part is going to take up this part of the spectrum, and Z is going to pick up this part of the spectrum. Notice that the relative brightness, so you would subtract the brightness that you get in G with the brightness that you get in R. The relative brightness for something locally is they're basically the same, right? The green filter, it's a little bit lower in green than it is in red, but the green is a little bit wider than red, and so this amount of light that you get in the green is roughly the same as the amount of light you get in the red. On the other hand, if you're looking at a galaxy that's farther away, the light has been stretched out, then you'll see that this transition, you can imagine that this edge is lining up in the red, and so you get very little in the green down here, and you could get a lot of light in the red. And so as this feature gets stretched out as you go to more and more distant galaxies, it will appear in different locations relative to the filters that you observe. And you can use the changing brightness in the difference between green, how bright an object appears in the green and the red, or the red and the infrared, or the infrared and the far mid infrared, so in the I filter and the Z filter, as a way of measuring that redshift without having to take a spectrum to identify that feature itself. So these are called photometric redshifts. So photometric redshifts was a big ingredient that went into doing these measurements. How do we get good, precise photometric redshifts? Because then you don't have to have a graduate student or an undergraduate student plugging in millions of cables over time, and you can just do your survey and you get the information that you need out of the redshifts. So there is a plot that shows, I guess it's this one here. Andromeda is the same as the Milky Way. It's basically the same age. All right, so photometric redshift analysis in the dark energy survey science verification data. So this shows you the photometric redshifts. So these are, I suspect that these are different groups that did different ways to analyze the data to reproduce photometric redshifts. So it's like, oh, we have a way of analyzing the data that's going to give you photometric redshifts, and ours is amazing. And then another group says ours is even more amazing. And so then what they did is they took actual spectroscopic redshifts. So that's this Z spec. So Z is redshift, and then spec is from spectrum. And then this is Z phot, which is the photometric redshifts, which is basically just you have these 4 filters, and then you excuse me, then you do the math on those filters to reproduce it. And if everything was done absolutely correctly or absolutely perfectly, then they would lie on this line. So redshift 0.8 would or spectroscopic redshift of 0.8 would correspond to a spectroscopic redshift of 0.8 would correspond to a photometric redshift also of 0.8. So you want the things to lie on this line because that's an indication that you're getting the right answer. There's going to be some spread, so clearly there's some spread in the photometric redshifts relative to the spectroscopic redshifts, but they do lie on that line for the most part. And then you're going to have a bunch of like this ensemble of things that don't match up. And so you just, as long as you know going in what your sensitivity is and like what the distribution looks like, you can account for that in your statistical analysis, because these surveys are not analyses that are done really on individual objects. They might discover individual objects that merit further scrutiny, but for the most part, these are, you have a gigantic ensemble of things. You don't study individual objects, you study the statistical properties of everything. And as long as you understand your uncertainty in measurements, like as long as you can characterize your uncertainty in measuring the redshift in a particular way, you can account for that in the statistical analysis. And so you can still get good results even though you have some things that are quite wrong, right? So here, the photometric redshift of this particular object with this method was off by a factor of 5, it looks like, from 0.2 to 1.1, factor of 6 almost. So anyways, this is what a photometric redshift did. It allowed them to just take the survey and quickly go across the sky, and as a consequence they can scan deeper, they could do multiple passes in order to get what they needed to get. So that is an important thing that happened with the dark energy survey that did not happen with the Sloan Digital Skies survey, which instead used a spectrograph. Galaxy clustering. Okay, so that is photometric redshifts. That's an important thing. So now, when they take measurements of supernova, so you take a look at the supernova. I think I had a supernova image up here somewhere. Here's the supernova image. when they take these images of the supernova, they can measure the brightness of that supernova over time because they can revisit that site multiple times because they don't have to take spectra. They don't have to plug these things in. So they can revisit this site multiple times. They can watch and track the brightness of these supernova over the course of usually like a month or so. And as a consequence, they can measure how bright, the intrinsic brightness of that object. And then they can use those photometric redshifts to get the distance or the redshift of that object. And the important thing that they want to measure is how does distance change with redshift? That's what they want to measure, is how does distance change with redshift, because that gives you the expansion rate with redshift. So when it comes to the supernova data, when you have, here's a supernova that goes off, the light is going to spread out in all directions. Okay, and as that light spreads out, it is going to fall as 1 over r squared. The intensity of the light is going to fall as 1 over r squared. So here's the explosion, here's the light coming out. The reason it falls as 1 over r squared is because the energy has to be conserved. And so the energy leaving one volume of space has to correspond to the energy leaving, the energy leaving some surface in space has to equal exactly the energy leaving some other surface in space, and surface area grows as r squared. And so you have the intensity, which is energy per square meter. The intensity is what you see with your eye, and it has to coincide so that when you have square meters of surface area out here, you multiply that by meter squared and you get energy, and energy is a conserved quantity. So this meter cancel that one. So that tells you that the intensity itself has to fall off as 1 over r squared. That is in the absence of the expansion of the universe. As the universe expands, it's actually going to take these light rays and spread them out. Okay? Or if the universe is collapsing, then it's going to take these light rays and it's going to concentrate them. And so when you're talking about light propagating through gigantic volumes of space, if space is expanding and contracting and jumping up and down and causing all sorts of problems, then the light rays are going to follow that. They're going to expand and contract along with the universe. And so the intensity that you get is not going to coincide with 1 over r squared. Or I guess the difference between what you observe and this 1 over r squared law is the anomaly that you're looking for, that tells you about the behavior of the universe. The distance you get from 1 over r squared from a supernova, this is the luminosity distance. So you have an object, you know how bright it is, you know how bright it appears, and then you can use this 1 over r squared relationship to get to make an estimate of what is the effective distance that the light has traveled since the time of the supernova before arriving at my telescope. Here's your telescope. And if you have supernova that went off at different distances, so here are the different distances that the supernova could go off. This one, the light's going to come out and concentrate. Here it's going to come out and concentrate. Here it's going to also, but here it's going to spread out more at the beginning, and then it'll concentrate a little bit at the end. And so you can map the overall shape of the universe by getting the redshift to these different objects, how long ago they went off, for example, because you can map redshift onto time, how long ago they went off, how bright they appear, and track the expanding and contracting properties of the universe. That is the luminosity distance. So the Sloan, or the Dark Energy Survey, is going to do a supernova survey to get the luminosity distance and monitor the expansion of the history of the expansion of the universe as a function of time. Okay, the number 2 survey that it's going to do is called Baryon Acoustic Oscillations. Baryon Acoustic Oscillations, which is BAO. Okay, BAO, Baryon Acoustic Oscillations. Baryon is just like regular matter. So that's protons and stuff like that. Acoustic oscillations is exactly what it sounds like. It is sound waves. So you have the early universe. Here's the early universe. It's a big blob of plasma. All this stuff's going around. Dogs and cats living together. Sound waves are propagating around. Those sound waves are going to correspond to overdense regions. So you're going to have regions that are overdense. You're going to have regions that are underdense, and then you're going to have other regions that are overdense and other regions that are underdense. So you're going to have these sound waves, overdense and underdense regions, and you have 2 different things that are interacting with each other. 2 different things that are interacting with each other. One of them is gravity that couples to dark matter. Okay, another thing, and that's actually where the sound waves come from, is regular matter, and that interacts with the electromagnetism, with the electromagnetic force. So this is regular matter. Regular matter. So there's a slight difference in the behavior between the regular matter and the dark matter. So as these sound waves are propagating around, the regular matter is going to start to collapse and fall into clumps of dark matter to form galaxies. But you're also going to have these sound waves, and so when you have a sound wave here, where you have an overdense region here where galaxies might form, one wavelength later, you're also going to have the other, like another compressed region from those same sound waves, and that is going to pull in dark matter. So you get a back reaction with dark matter is going to create, dark matter might force a galaxy to form in a particular area, but that is going to be part of a sound wave in the baryons, where they interact with the electromagnetic field, and therefore they can set up sound waves. You can't set up sound waves with gravity. Gravity doesn't work that way. There's no repulsive force with gravity. So the baryons will create a sound wave. So you'll form a galaxy here where there's dark matter that kind of nucleates it, but that's going to be part of this broader structure of sound waves that propagates only through the baryons. So now you're going to have an overdense region of baryons. Dark matter is going to fall into this region, and there's some probability, some excess probability, that you will form a galaxy at this distance, another galaxy at this distance. So if you see a galaxy here, there's some excess probability of forming a galaxy here. Now this is going around in all directions at the same time. It's not just in one location. So you have a sound wave that propagates out in 3 dimensions, and so you're going to have a shell of material. So if you form a galaxy here, baryons are going to fall in, they're going to create sound waves. The sound waves are going to propagate out. Here's the distance that they propagate. They propagate up until the time that the baryons decouple from the photon field, from the electromagnetic spectrum. So you have these particles that are going out, they're interacting with each other through the exchange of photons, but then when the universe cools to the point where those photons are able to escape, you no longer have a way of, they don't interact the same way. The pressure basically disappears. It's not a plasma anymore. And that is going to give you a distance, this distance right here, which is like 500 light years, 500 mega light years, million light years. That's a light year, by the way. That distance is the distance that sound propagated from the Big Bang up through the time where the universe cooled to the point that the electrons and protons combine together to form neutral atoms. And so then the photons escape, and you remove a lot of the coupling that allowed the sound waves to propagate in the first place. Okay, so that means you form a galaxy here, it's going to send out kind of a sound wave in the baryons. The dark matter is going to respond to that sound wave in the baryons, and you have excess probability of forming a galaxy here because there's a slight overdense in the material. So that is the thing that institutes baryon acoustic oscillations. Baryon acoustic oscillations were discovered by Daniel Eisenstein, who's now at Harvard. At the time, he was at the University of Arizona. So if I look at baryon acoustic oscillations, BAO-in-SDSS, the Sloan Digital Sky Survey was the first place that baryon acoustic oscillations were discovered. These are the data right here. Excuse me. These are the data that showed this excess probability. So this is the galaxy-galaxy correlation function, if I remember correctly. So this says, if you have a galaxy in a given location, what is the probability of finding another galaxy at some distance, at some separation? So this is the co-moving separation over here. Don't worry about the H inverse megaparsecs. That's a way of converting units. So if you have a galaxy in a single location, the chances are that there's a good chance that you're going to find, now this is a density, so it can go higher than 1. You integrate the probability in order to get the total probability. So if you have a galaxy in a given location, there's a good chance that it has a neighbor. That's what this shows. At no co-moving separation, so right next to you, there's a good chance you're going to have another galaxy. As you get farther and farther away from a galaxy, the probability of seeing a second or a third or a fourth galaxy is going to drop down, because galaxies form in given locations, and there's going to be voids that open up in between them. So for example, with the Milky Way galaxy, we do have a nearby neighbor, the Andromeda galaxy. So that would be like the Andromeda galaxy. As you get further away, you get to the Triangulum galaxy, but the density of galaxies goes down. So after you get past the Triangulum galaxy, there are hardly any galaxies, and you get out at these distances until you arrive at some other cluster where there's another galaxy, it's got a neighbor, and so forth. So this tells you basically the probability of finding a nearby galaxy at, now this is separations of megaparsecs. Okay, so the Andromeda galaxy is at 2 megaparsecs, which is like way down here. So this says there's a good chance of finding another galaxy nearby, and that chance declines rapidly, and it declines very rapidly. This is a log scale on this axis, right? So it goes from 1 to 0.1. So this is 1/10 the probability. From here to there is 1/10 the probability, and then this is like 1/100th of the probability down here. So keep that in mind, that this is a log scale on this axis. Okay, so then the idea is if you have these sound waves propagating out and the dark matter reacts to that, and then as a consequence you form a galaxy at some other distance, there's excess probability of seeing it, that shows up right here. So this bump right here that you see, so the probability goes down. These were actual measurements taken from the Sloan Digital Sky Survey. They saw that when you look at the separation of galaxies in the sky, that you get this bump. That bump corresponds to basically the wavelength of sound that fits into the universe from the time of the Big Bang until the time of recombination. And there are excess galaxies that form at that distance. That corresponds to a very specific distance in real space. So it's basically the wavelength of sound that from the early universe, and then the universe continues to expand up to the point where you get to 300 and something, 400 and something light years, right? This is H inverse megaparsecs. A megaparsec is like 3 mega light years. Okay, and then it's H inverse, and so you have to scale it up because H inverse is a number that's like 0.7 or something. Okay, so these are the galaxies that you see that form as a consequence of the reaction of these sound waves in the very early universe, and then how that is imprinted on the galaxy structure as you go forward. What this gives you is not, it gives you a different measure of the scale of the universe. So now, if we look at the scale of the universe, with a supernova data, we got the luminosity distance, which is how distant is some object if you assume that light falls as 1 over r squared, which we know that it doesn't because the universe is changing its shape. In this case, we have a ruler. Okay, so here, if we see a galaxy here, we can do this galaxy-galaxy correlation function and measure the location or the size of the ring or the shell of galaxies that form near some cluster. So here's all these different galaxies. You say, okay, here's a galaxy. What's the probability of detecting another galaxy over here? And you measure that distance. You measure that peak. And you do it at different redshifts. So here's your camera down here. Here's your detector looking up here. And this could be at redshift 0.1, for example. And you do that galaxy-galaxy correlation function, and you observe this peak right there. And you see where it lands. And then you do the same thing here at a different distance, 0.5. And you see the peak, and it lands at a different location, or spatially separated. You know that this corresponds to a very specific wavelength from the early universe that stretches with the universe as the universe expands. And so if the universe contracts, then maybe if there's a period of contraction, you come up to a redshift right here, and you see that the peak, instead of having this separation, that peak is now here, and this peak is up here. And so then you can map, as you go back in expansion history of the universe, you can map how this peak has changed in this location relative to each of the galaxies, and you can map out the history of the universe, how it's expanded and how it's contracted. That is Baryon acoustic oscillations. That's the angular diameter distance. Angular diameter meaning like how big of an angle does something make on the sky, and that's how you get it. That's Baryon acoustic oscillation. So that's another important signature that we have for the expansion history of the universe. So we have the luminosity distance, history of the universe, and now we have the angular diameter distance for the history of the universe. There are two other important features that we get that constrain the properties of dark matter and dark energy. One of them is the clustering properties of galaxies. So basically the idea is dark energy is trying to pull things apart, dark matter is trying to pull things together. And so if there's a lot of dark energy relative to dark matter, then the galaxy clusters are going to be more spread apart. It's going to be harder to form galaxy clusters. So because the universe is trying to pull them apart from dark energy, and gravity from dark matter is trying to pull things together. So if you have a lot of dark energy, then you're going to have more diffuse and more widely separated galaxy clusters. If there's a lot of dark matter relative to dark energy, then you're going to get tight clusters that are closer together from each other, closer together to each other. Does that make sense? Closer together? I think just closer together works in that case. So you can look at the clustering properties of galaxies as a function of redshift. So you go back in the early universe and see, okay, what is the galaxy clustering properties here? What is the galaxy clustering properties at some different distance? What are the galaxy clustering properties at this distance? What are the galaxy clustering properties at this distance? And you have to run these through computer simulations to model like what would happen if you change the composition of the universe slightly. How would the galaxy clustering properties change? But then you can again reconstruct the history of the growth of these things in the universe and constrain the properties of dark energy. So that's 3 different ways of constraining the properties of dark energy. Thank you for that, Sub. I appreciate it. Number 4 method for constraining the properties of dark energy is related to how does matter cluster together? And that is through the weak gravitational lensing. So here what's going on is you have, I think I have an image. Let me see if I have an image. That is not it. That is also not it. That is not it. Okay, so it's none of those. Let me see, maybe it's in here. No, okay, so I'll just describe it. Okay, so if you have here's you with your telescope. You have some galaxy right here, some galaxy cluster, and you have some distant galaxy over here. Very distant galaxy cluster. The light from this galaxy is going to be distorted or bent as it goes by this galaxy cluster because gravity is going to affect the trajectory of the light that goes by. So space-time gets warped and light travels on a straight line in space-time, and because space-time is warped, then that means that the light path is warped. So when you look at, if you look at just galaxies in general, so here you are looking at space, you're going to see galaxies kind of like this in random orientations. But if you have a bunch of mass that's kind of in the middle of this, then what you're going to see is that the galaxies are going to tend to align. They're going to be distorted in their shape, something like this. I mean, you'll still get things that are turned slightly, but they're going to be wider in this direction than they are in this direction. So they won't be randomly oriented anymore. Okay, so random orientations, if there's no matter, if there's no intervening star cluster, then there's random orientations. Not star cluster, if there's no intervening galaxy cluster, then there's going to be random orientations. If there is an intervening galaxy cluster, then you get these correlated orientations of the shape of the galaxies. They're going to be flattened out. And they're going to be flattened out. The degree to which they are flattened out tells you about the matter that is concentrated in this galaxy cluster. So if we look at weak gravitational lensing, let's take a look, see if we can see a good image of weak gravitational lensing. Gravitational lensing. And of course, they show exactly not what we're talking about. So this image here is strong gravitational lensing. The difference between weak gravitational lensing and strong gravitational lensing is basically, in weak gravitational lensing, you take an object that's basically circular and you turn it into an ellipse. So that's weak. If strong gravitational lensing is when you take an object that's roughly circular and you turn it into a loop or a ring like this. That is strong gravitational lensing. It's distorted beyond the first multipole expansion, or first expansion term in a multipole expansion. So you can't describe this as an ellipse. It's too distorted to be described by an ellipse. That's the difference between weak and strong gravitational lensing. So ignore this because that is not weak gravitational lensing. This is weak gravitational lensing. So here are a bunch of galaxies randomly oriented. Here is the signal that you get from an intervening galaxy cluster with the lensing. So you look for these things. Now you go into the sky, you look at the orientations of different galaxies and how those orientations relate to each other. So the angle that you have for different galaxies, how they relate to each other, and that tells you about the matter density along the line of sight. And because you're measuring the redshift to all of these galaxies, it gives you where clumps of dark matter are located as a function of distance. And that also tells you about basically the growth of the universe. So those are the 4 probes that the Dark Energy Survey is designed to use to constrain the properties of dark energy. It is supernova to get the luminosity distance as a function of redshift, because redshift is the observed expansion of the universe, how much it's expanded between you and that object. And then you measure the luminosity distance as a function of redshift to get the history of the universe. You use the angular diameter distance to get, so from Baryon Acoustic oscillations, to measure the shape of the universe as a function of redshift. You get the growth of galaxy clusters with time to measure the clustering properties of the matter in the universe. That is a competition between dark energy pulling things apart and matter pulling things together, gravity pulling things together. And you get the weak lensing measurements. All of these things constrain the properties of dark energy as a function of time. Constrain the properties of dark energy as a function of time and allow us to measure this equation of state parameter W, that if it's less than -1, so like -1.1, we're all going to die in the future, or our great-great-great-great-great-grandchildren are all going to die in the future as they get ripped apart as the universe expands out of control in the big rip, or if the universe really is flat and the equation state parameter is what you get from a cosmological constant being -1, that is what the goal of this survey is to see. So let's see what results the dark energy survey has. Dark energy survey results. They're kind of in the middle of the survey. I don't think they finished yet. So let's see if they have any. They've got 3 years of data. News and results. Not really a whole lot to see here. So let's go with dark energy survey results. Let's go to images. Press releases, dark energy survey. Okay, it's a little bit low resolution, but that's okay. We will survive. This sigma 8 is related to, I think S8 is the size of the quantum fluctuations in the early universe that eventually seed the dark matter halos. This is omega matter. So omega matter is the density of matter in the universe. That includes both dark matter and regular matter. And so this says, dark energy survey year 1 says that the size of the fluctuations and the regular matter in the universe live in this area here, and then Planck measurements put it over here, and then when you combine the two in a combined measurements, you get basically what we already knew from previous results, but it confirms the previous results, that matter is roughly a third of the energy density of the universe is in regular matter. And that, okay, so this is not a term that most people are familiar with. If you're a cosmologist, then you care about that, but the regular matter part you do care about. That, or I'm sorry, the total matter part you do care about. How much total matter is there in the universe? All right, let's take a look at, see if they have any other results that are important. This one looks important. This is the supernova results. First cosmology results using type 1 supernova, presumably also from the dark energy survey because it says DES in it. Okay, so again, a low resolution image, but we'll work with it. So dark energy survey. So the low Z stuff, that was done by the early supernova measurements. So that was Sloan Digital Sky Survey and the Legacy Supernova Survey and some of the early stuff that was like the High Z Supernova team, the ones that got the Nobel Prize for doing that. That's all fairly low redshift stuff. That's right here. The dark energy survey is looking at higher redshift stuff between 0.1 and 1. So that's, their measurements are up here. And then they have, what are the best fit line? What is the expansion history of the universe in now using luminosity distance? And it looks like, lo and behold, they agree, or you do get a deviation from a model where it's all regular matter. So the blue line is all regular matter. So the blue dashed line right here, all regular matter, no dark energy, and no equation of state. So this W is the equation of state parameter. So this, it's kind of hard to see because it's, even though this is supposed to be a gigantic, it's supposed to be a huge image. Let's see if we can pull it up in all of its power and glory. There we go. That's what we're talking about. Okay, now we can zoom way in. Okay, here we go. Good, move this over. All right, so this triad of numbers is omega matter, how much regular matter there is, omega lambda, how much dark energy there is. Those typically add up to 1. And then this W parameter, again, that's the equation of state parameter. That's what Dark Energy Survey wanted to measure. So it's showing a few examples. So here are the data. The data are the red and the orange points. With error bars, you can see the error bars on there. They're tiny error bars in these results. And it's showing what are different possible universes. What if we have a universe that's all matter, no dark energy, and as a consequence of no dark energy, there's no equation of state parameter. So this is basically a third of the energy density in regular matter, which is what we get from the growth of clusters, and no dark energy at all is the green curve. Okay, seems to go kind of through the data, but if you look at the anomaly down here, so this is when after you subtract out the line, you get this. The green curve is way south of all the data. The data are up here. The green curve is too far to the south and therefore is excluded with some confidence. What if we lived in a universe that was all regular matter? So we know from the cosmic microwave background radiation that the universe is flat, and so the total of omega matter and omega lambda has to equal 1. So this is basically what you get from clustering properties directly. This is what you get from, if you assume that the universe is flat and it's all matter, then you get this omega equal 1, and that's even further south of the data. It's too far away from the data to describe the data correctly. And so then you say, okay, what if you have a mixture of dark matter and dark energy? So now you have something that's, this lower one here, the one that misses the most, is where you assume that when you say, we know that the universe is flat because the cosmic microwave background radiation tells us that it's flat. This one is what you get from the clustering properties of matter that says, or the clustering properties of galaxies that says that omega matter is 0.3. And so neither of those agree. You have to have dark energy. You have to have some dark energy. This would be consistent with the cosmic microwave background radiation. This would be consistent with the growth of clusters, but they're inconsistent with each other. But having omega matter of 0.3, omega lambda, so that's dark energy, of roughly 0.7, those two things now go through the middle of these data like this. You can see how well that line, the gray dashed line, goes through all the data. And that is how we know what the universe is made out of. And we get an equation of state parameter measurement of negative 0.978. I don't know what, doesn't say here what the uncertainty is here, but it should show up. Whoa, that's a big. Okay, so there's some uncertainty here, and I suspect that uncertainty includes -1. So, but this is pretty close to -1, which is what you'd expect from just generic dark energy. All right, on this side, this is showing the equation of state parameter. So you can see how close it is to -1. It does actually overlap -1, basically right in the middle of it. And this is showing omega matter. So this is how much regular matter is there from the cosmic microwave background radiation, that's right here. And from Dark Energy Survey Supernova Year 3, statistics plus systematic effects. So the statistical uncertainty is just from the number of data that you have. The more data you get, the smaller that will get. The systematic uncertainties is, you know, how well can you describe whatever things are complicating your analysis. That could include your ability to measure the photometric redshifts accurately. Okay, so that's 3-year data, and when you combine the two, you combine the cosmic microwave background radiation with the supernova data, then you get this one ellipse that corresponds to an equation of state parameter, which is the parameter de resistance is right there, and you get -1, which is basically says dark energy, to the sensitivity of our measurement, dark energy is consistent with generic cosmological constant type thing. So there you go. That is the Dark Energy Survey. That some of the results from the Dark Energy Survey. Other things that come from the Dark Energy Survey, it finds asteroids. There's asteroids that are discovered all the time because it's surveying the sky, and so you're going to see everything that moves in the sky. It probably sees lots of satellites. It's going to see even more satellites now. So there you go. Let's see if there's any other results from Dark Energy Survey that are going to be worth looking at. I don't know what this is. Probability redshift. Okay, I don't know what that one is. There's the tank in the sky. There's the tank in the sky relative to the galaxy. So here's the Milky Way galaxy. You can see that they avoided the Milky Way galaxy because it would contaminate things. Okay, well, so there we go. That is the Dark Energy Survey. That's the kind of thing that you get from these. Here we go. Here's a year 1 result. What does this show? This is okay, so this is worth looking at. Excuse me. Oh, and that's probably also worth looking at, that one right there. So let's open up this one in a new tab, and we'll open up this one in a new tab, and we'll look at these two. So this is Baryon Acoustic oscillations plus Big Bang nucleosynthesis. Big Bang nucleosynthesis is, we've talked about that one, the formation of the light elements in the universe. Planck gives us this, so that's the cosmic microwave background radiation. In this case, it's looking at the Hubble constant. What is the rate of expansion of the universe? The Hubble constant, it's historically been around 0.7. It looks like it's getting a little bit smaller. So the Planck results are right there in that ellipse. Dark Energy Survey gives this kind of big floppy ellipse. So it's not a very good constraint on H, but it is a good constraint on omega matter. That constraint on omega matter comes from the growth of clusters of galaxies, how much matter there is that forms these galaxies. So that's why dark energy survey, it's a relatively good constraint on omega matter, but not a very good constraint on this H. You can see that it's skinny in the vertical direction, which is omega matter direction, and it's fat in the H direction. Baryon acoustic oscillation and Big Bang nucleosynthesis gives us this thing, Planck gives us that thing, and so when you combine all these things together, you get basically the expansion, the Hubble constant is 68 kilometers per second per megaparsec, something like that, some quantity like that, and omega matter is right near, like between, so there's like what, 0.27, something like that, when you combine these together. More measurements and better control of systematic effects will probably bring these things into even better agreement. This figure here is omega matter and omega lambda. So this is the matter density in the universe and the dark energy density in the universe. And you can see this is going to be Planck again, the cosmic microwave background radiation. Supernova results are going to be there. Baryon acoustic oscillations is this vertical one. So that's basically also kind of related to the growth of structure. And all of these ellipses kind of overlap right around here in this point. So you add a whole bunch of stuff together, you add all these things together, and they all overlap right around there, which is 0.7 for dark energy. 70% of the energy density of the universe is dark energy, and roughly 0.3 for regular matter. There is a little bit of disagreement, but now we're getting to the point where as our measurements with each individual probe, so supernova and CMB and stuff like that, with each individual probe, as the uncertainty or as our measurement precision gets better, then the systematic differences come into play. Like, what are the things that are contaminating the CMB measurements that we didn't have to account for before, but now that our measurements are getting more precise, now we have to worry about systematic effects. Now we have to worry about the fact that some galaxy cluster in some distance is going to lens the cosmic microwave background radiation, and that's going to make it look brighter in some location than it actually is. Or, you know, the supernova results, you know, as maybe there's a piece of physics that we haven't incorporated into our supernova models, and therefore we don't actually understand how intrinsically bright supernova are. It adds some uncertainty to the thing. And if we want to make improvements in these measurements, then we have to have better models of the supernova results, better models of how supernovas actually shine. All of these things, as our measurement precision gets better, it's going to force us to deal with, you know, our telescope is flexing. As we tilt over to the side, the telescope flexes a little bit, and that causes a distortion in the shape of the galaxies that we observe. And that's going to creep into the weak lensing measurements. So all of these things are going to force us to refine our measurement processes and the theory that goes into explaining them, because we only live in one universe. So at some point, all of these ellipses need to agree with each other. The extent to which they disagree with each other is either a consequence of not having enough data or having some systematic effect that creeps in that biases our data to one side or the other. So that's what we can expect going forward. The Large Synoptic Survey Telescope, which is now the Vera-Rubin telescope, that's kind of the next link in the chain. There's another survey that's going on, or that's being built right now, called DAISY, which is it is a complement to the Dark Energy Survey, but it's built at the Mayal telescope, which is a sister telescope to the Blanco telescope. So the Blanco telescope is the one in Chile. The Mayal telescope is in Arizona, and DAISY is that's another instrument I'll have to talk about at some point, where they're actually doing spectrographs. So they're doing spectrographic measurements of the redshift, so they don't have to worry about photometric redshifts. But so they don't have to do all the plug plate stuff. They have little actuators that will point the fiber optic fibers where they need them to go. So that's something for a different stream. Okay, so there we go. That is the Dark Energy Survey in all of its power and glory. They've had a lot of results that have come out recently. I didn't really get into a lot of their results, but they've already released their third year of data. They're probably in their fourth or fifth year of observations. And so we can expect to get more results from them going forward for the next few years. So pretty cool. Anyways, I'm happy to answer questions at this point. Let's see. Planck is a project to collect the data. So cosmic background radiation, Planck is the current instrument that's up collecting data on the cosmic microwave background radiation. Let's see. We've got, what else do we have? When you say the CMB is flat, what does that mean? When I say that the universe is flat, that means that the total energy density, whether it comes from dark energy or from dark matter, that the sum is equal to 1. The sum of dark energy and dark matter density, the dark energy density and the dark matter density, they sum to 1. That implies a flat universe, meaning that 2 parallel light rays will propagate next to each other forever. If you have an open universe, then they will split apart, and if you have a closed universe, then they will pinch together. So having 2 parallel light rays go parallel to each other in perpetuity indicates that the sum of the dark energy density and the dark matter density is equal to 1. That's what I mean by flat. That's what it means cosmologically speaking for it to be flat. Okay, let's see, what else do I have on here? What's the tank in the sky? The tank in the sky is just the observation footprint of what they're doing. How about Earth? Universe is flat, but the Earth is not flat. And I actually have merch. I have merch that shows that. Let's see. Designed by humans, Horizon Psi. I have merch that shows that the universe is flat. What? Where is it? Right here. Here you go. The Earth is round. This is round. See, round there. And the universe is flat. There's the flat universe. So yes, I have that. So if that omega value is actually minus something, it would suggest a big crunch. So you're correct. The fact that the omega matter, if I can find that again, that's not it. That's not it. Is it this one? No, whatever it was. Yeah, the fact that this is not exactly equal to -1 implies a big crunch. However, notice that the error bars, the uncertainty, overlaps with 1. And so no one's going to claim that this is statistically significant. The difference here is not statistically significant. The uncertainty is larger than the distance from -1. The uncertainty of the measurement is bigger than the separation between -1 and the value that's actually at the center. So